Well, thank you everybody for joining me. We have a few stragglers coming in, late joiners. We're just now getting started. So I'll go through my short introduction. I'm sure some of you have heard this before, so I've kind of truncated it down to one slide. I'm Hannah Arnold, the customer representative for EngineSoft. Before this, I was an engine builder for several performance shops and was the head fabricator and mechanic on a two-time champion race team. So I'm glad to be here and be working with everybody, customer-facing representative. Today we're going to be talking about optimizing dynamic mechanisms. This will be presented by Dr. Brant Ross. We'll be having a Q&A after the session. You're able to submit any questions during the presentation to Zoom and YouTube. Keep in mind, if you're on YouTube, you must be logged in to an actual profile in order to be able to comment. So if you're just logged in as anonymous and you're watching it, you won't be able to actually submit anything. So with that, I'm going to go ahead and turn it over to Brant, and we'll get started on the Optimizing Mechanisms webinar.
Okay, great. I hope everybody can see my screen. So yes, I'm Brant Ross, Chief Solutions Officer with EngineSoft USA, which means I have the great opportunity to work with clients on helping them solve their simulation needs for their products, both with moving assemblies as well as fluids problems. The presentation today on optimization actually is taken from a presentation that Sungtae Kim of Function Bay gave at the Case 20 conference. So we've just kind of updated that a bit for you today. So first of all, before we get into optimization, let's talk about design a little bit, since frequently we do refer to design optimization. So, in the design process, we have to look at various concepts, but when it comes right down to the main function of design, it's all about making choices. So looking at the different options, of which there are many, and then developing, selections of all those different options such that they meet the design requirements. And if we can meet all those design requirements, then we can consider that we've had a successful product development process. So in the case of this dune buggy, some of these design requirements might be, being able to fit 2 seats side by side, being able to handle driving on a rough road, certain velocity threshold has to be met, keep the overall size within a certain limit so it can fit on a trailer, and then issues with materials and shapes as far as the styling, and so forth. And of course, a lot of the characteristics have to do with the cost aspect. So that'll determine some of the selections. So design is to make the choices, and basically choices need to meet the requirements, but then the question is, can we come up with the best set of choices? And, practically speaking, it's not typically possible to include every possible choice, within the optimization, but rather what we have to do is consider all the different choices, and then we have to decide which ones we want to study, and then we would hold the other aspects of the design fixed. And that's what people typically do, and people have been able to have great results with that approach. I'm just saying that we should understand that typically with optimization, we're not guaranteed to have the exact perfect design, because typically it's impossible to consider every aspect of the product all at one time. But people have been able to come up with great improvements in performance. So what are some examples of optimization that we're familiar with? So in the case of, for example, choosing a restaurant or choosing a meal at a restaurant, we have to make these, trade-offs and decide, okay, what kind of taste can we achieve, and how much food is there, and then that might be compared, to the cost. Transportation, we're looking at the time to get from point A to point B, and then trade that off with cost and convenience when picking the different modes of transportation. With our work tasks, we have to look at priority of tasks versus urgency of the deadlines, and also our own efficiency. And then finally, with things like exercise, we have to decide, okay, what's the best exercise to pursue? How much time does it take? And how beneficial is it to us? So I think these are all familiar examples of doing an optimization in our lives. So when we look at optimization, as we look at this, top view of this valley in this mountain range, what we can do is say, okay, our optimization is to try to get to the highest point in that mountain range. And so to do that, we have to look at, first of all, design variables. Those would be the inputs that we can change as far as pursuing getting to the highest point. The objective function is to figure out what is the highest point. In this case, the objective function would be elevation. And then the constraints would be what gets in our way. So in this case, we can see these design variables being the X, Y, and Z coordinates. We can see kind of the lowest point, steepest point, and so forth. And so again, we have to pick what we're trying to achieve. Constraints would be the areas we have to avoid. So if there's some kind of marshland that would be hard to hike through, we have to avoid that. We'd be avoiding residential areas as well. So in the case of optimization with real design, there's different types of optimization. So one is size optimization, where we're actually just changing, basic dimensions. And then, basically with the size optimization, we're typically trying to minimize the overall volume of the part or the set of parts. And, also looking at trying to minimize loads or stresses. Constraints would be, limitations on the different dimensions, and also there could be constraints on maximum loads. So in the case of parameter optimization, that's quite general. So any type of parameter could be used. Could be different attributes of different machine components like springs. And the objectives could be a variety of things. And here we have examples of vibration issues that are trying to minimize that or maximize some kind of performance. Might be the speed of doing a certain operation. And the constraints could be maybe limitations on what kind of attributes, component attributes can be purchased or are available from suppliers. Shaped optimization is to actually change the actual shapes of parts, which some cases is done with finite element mesh. So you may be using certain surfaces to control volumes of interest and remeshing and so forth. Like the last one here, topology optimization is used with finite element analysis, where you're actually removing elements from the simulation, at least removing their effect, and then coming up with a different shape because of, the remaining shape has to do with the remaining element set. So in going through this optimization process, we have to first formulate the optimization problem. So as I mentioned earlier, this would be where you decide what are the design variables that we're going to let change versus the design attributes of the product that we want to keep fixed. And then the performance indices are the performance, the outputs basically from the simulation. What can the system achieve? And then once you have narrowed down which design variable is going to use, then some of the performance indices become objective functions. Other performance indices may become constraints. And also there's a need to then pick reasonable ranges that the variables can vary within. And actually the selection of ranges is very important, because if the optimization problem includes ranges that go outside of bounds such that the system will no longer function, then that can be problematic for coming up with proper data to optimize. Okay, then the second step is actually applying the parametric modeling in the software, and likewise formulating the performance indices. And happily we'll be seeing that this is done using standard tools that you're used to with the Recordine software. And then third step is to actually select optimization methods. And we'll see that with the AutoDesign tool, a lot of that is actually automated. So what are some of the challenges in the formulation of the problems? So first, deciding which design variables are going to be changing. And that has to do with, figuring out, where the highest sensitivities are. Performance indices are fairly straightforward to understand, but may be a bit challenging to define within the modeling environment. Have to classify these design objectives versus constraints. And we'll talk more about constraints, but basically constraints are where we define certain boundaries that can't be crossed. And so we just have to look at the problem and figure out which attributes fall in that area. And then figuring out these ranges can be a challenge. And actually it could be a surprise that maybe some certain combination of design variables may cause a system that won't actually run to completion. But if that's detected, then it's just a matter of adjusting the range and rerunning, and then formulating the performance indices. So we'll see examples of all these things. As far as the numerical optimization itself, one of the challenges is that you want the optimizer to be able to select the global optimum and not just some kind of local optimum. So if we think back to that valley scene, there are certain places that might have been locally a high point, but not the overall high point on the range. So, basically we need to cover a big enough range in the design space so that we can, basically see the global, where the global optimum, what vicinity it's going to be in at least, which has to do with the sampling of the initial designer experiments. We'll show that, or we'll talk more about that in a moment. Second thing is selection of a solver. We'll see how that's automated. Third one is, we have to watch out for excessive runtimes. And, the runtimes will tend to go up with number of design variables and the objective functions being examined. But we'll see that we're doing some special things to keep that runtime under control. The last one is the scale difference of the performance indices. So in other words, if one performance output has a value between 0 and 1, and another one has a value between 0 and 1,000,000, what we'd want to do is apply some scaling to make sure that, we're weighting those things properly. But, the good news is that we can apply that weighting. So the main point here is, don't be afraid of trying out optimization. It's not a trivial thing to do, I wouldn't say, but we have done many things to make the process quite approachable. And one comment I'd like to make at this point is that to do optimization of your system, first you start out and you need to have your system in this case simulated with Recordine, and you want things to be running smoothly. And sometimes, once we get the model running and, we do some validation work, and then we can kind of call that good as far as just doing an assessment at a certain configuration. But in the case of optimization, you need to do all those things. But the other thing you want to do with the model is you want to be able to check out that as design parameters are changed, that the model behavior is changing in a fairly smooth way. And since many of the multi-body dynamics models are nonlinear, then sometimes small changes can have too big of an effect. So one of the things that you want to check is that the model basically is performing very smoothly. So things like contacts should be smooth, which speaks to the resolution of the contact itself. And you just want to check to make sure that everything has gradual transitions, as much as possible. Okay, so the next section here is to talk about the formulation and modeling when you do this optimization work. So the first thing to do is to set up design variables, and this is a table that just shows the things that you want to consider. So we have a list of these 6 design variables. Of course, in the actual model, you'd want to, have some names that are easy to associate. And then the next thing you need to do is to figure out what are the allowable, range of that variable. And actually, in the optimization process, where we start out by doing a design of experiments run. And so these ranges are used to decide, what configurations are going to be used in the design of experiments. So you want these ranges. It's very important that they be set as, best you can, because if you set them too wide, then the design of experiments is going to maybe cover a huge area, and maybe you're going to lose some resolution. And of course, you can always gain it back by doing more runs in the DOE, but then that takes more time. If the range is set too narrow, then maybe the location of the very best performance, will not be available. So it is worth it to take some time to carefully select, what are the reasonable ranges that can be considered. The current value is just starting value for all these different design variables. And then these last 2 columns are things that are sort of qualitative, but just some kind of ranking on, what it would mean. First of all, the cost to make changes, in that particular parameter, for your organization. And then the next one is the difficulty, associated with including it in the simulation. So, in this case, we could have like 3 variables that have to do with length, 3 with respect to an angle of something. Next one is performance indices. On this one, we want to be able to look at the different outputs of interest. Some of these outputs need to be constrained, but other outputs, need to be either maximized or minimized in order to get to the optimum configuration. And so if we have certain goals with these indices, then we can indicate that. And then the last column, again, the importance of including the performance output there, how important is that into the optimization of interest. So, clearly you want to make sure you're including the higher importance options there. So then sometimes there may be too many design variables. And so if that happens, what you want to do is look at this, the change cost and the difficulty. So in this case, it suggests that the design variable 6, should be eliminated, unless there's some special reason it has to be there. So, I mean, this kind of ranking can be helpful to figure out how to focus in. For the performance indices, what we want to do is to check on each one and identify whether or not there are limits, whether lower limit or upper limit. And the ones that have limits are typically best assigned as constraints. And then the ones that you just want to minimize or maximize, those should be the objectives. Sometimes if you have, something that's very important, then you want to set that to be the objective, the single objective. So if we look at these, the performance index 1 and 6, we can see they're both minimization. When we come to importance, the performance index 6, number 6 is the most critical. So, one option would be to make that the objective, and then the performance index 1, could possibly be expressed as some kind of constraint. And then likewise, a constraint could become an objective, again, when it doesn't have these limits associated with it. So in the case of PI5, it's actually, there's a certain target value, so that could be an objective. Okay, so now let's get to the specifics of applying these things. So in this case of this Truss Bridge, we have design variables that are set up to define X and Y components of different positions. So you can see of position 1, position 2 here. And another design variable is, stiffness. And in this case, spring stiffness may be associated with an attachment point between the bridge and the support. So in order to do that and define these physical quantities, for the outputs here, this is for the performance index, then we typically use expressions in Recordine. So this expression here goes through and adds up all the lengths of all the different members in this bridge. The reason you'd want to do that is that the cost of the materials would be a function of their length. So if you add up the total length, that'll give you a feel for the total cost. So you want to improve the performance of the bridge while not, raising the cost. So that's why you would want to track that cost. Other things are straightforward, looking at the reaction force of a joint. Velocity accelerations are all easily accessible with the expressions. Another thing you may look at is how long does it take to get through an operation. We'll see an example of that later. And then, things like stress and deformation can also be tracked with the expressions. So as far as, setting up the optimization method, actually, we can see here, this is directly from AutoDesign. There's different methods, different settings, but defaults are provided for everything. And like as far as the method is concerned, one option is just to say auto selection, and it will look at your model and it will figure out the best technique to use. as a function of what you defined for your design variables and so forth. Okay, let's get into AutoDesign. And AutoDesign is actually embedded within Recordine. Just one of the tabs in Recordine. And so it's very easy to use because you're staying in the same environment. You can see the different groups there. So defining the different parameters, input, output, optimization, tasks that you may want to run. Reliability is to do some things related to Six Sigma. And then there's a simulation history that can be accessed. So in Recordine, you may be used to defining parametric values, and you can map those directly to be design variables, and then that gives you an opportunity to add information such as the range of that design variable. And as I've mentioned, expressions are used to define the performance indices. So you're just creating expressions as usual and just selecting them from the list. So in the modeling process, AutoDesign offers, a good interface. It's compatible with all the other interfaces in Recordine. And again, a lot of automations included in it. And basically you just walk through the process of defining the design variables and objective functions. And then when you kick off the optimization, you're still within Recordine, and it'll be submitting all these mini jobs automatically, and you don't need to do anything other than wait for the results to come. So the solver for the optimization includes a meta model algorithm, and we'll talk about that. It came from Bayesian global optimization, and it's easy to set up multi-objective optimizations because you can set up as many things to be objectives as you would like to, and then it's just a matter of setting the weighting between those different objectives. And there's a lot of robust design techniques included. And there's actually a module for including things like tolerances. And also it's set up that if there's some, a little bit of noise, which, in a model there can be with impacts and so forth, there's numerical noise on the data, but because the way this is looking at a global approach, it doesn't have a problem with that. So there's various methods that are supported, but again, things can be automatically selected. But if you're having any difficulty, we can work with you to then manually, select a particular method to overcome whatever issue you may have. I should make a comment here about this this thing about the noise. I had somebody wanting to try Recordine with another optimization tool, and it did an optimization of a simple vehicle that we had put together to be able to climb up a hill. It was an off-road vehicle, and it did that optimization, and it required, I think, 800 runs of Recordine to solve it. And I redid it with AutoDesign, and it only required, I think I did initial like DOE of maybe 25 runs, and or maybe only did 9 runs. Anyway, I think I did 9 runs, and then when I went to do the overall optimization, it converged, I think, with 1 more run. So it was like 10 runs rather than 800. And the other optimizer wasn't necessarily a bad optimizer, but it was sensitive to noise. So that issue is important. And so this example here, AutoDesign was able to, with 116 analyses, optimize the design with 105 design variables and 14 performance indices. So that's fairly amazing. So how does it do that? So, basically the idea of the meta model is it represents an n-dimensional, design space that's mapped all the design variables. So you run the DOE, and with the DOE results, that's used to come up with the n-dimensional meta model. And then once you have that, then you can optimize with the meta model and find the optimal point. So then what happens at that time is once you have the optimum, then AutoDesign will automatically do one more run at that optimal point, and then it will check to see if the predicted behavior exactly matches the actual behavior, from Recordine itself. And if it does, then the optimization is done, and it gives you the result. But if it's not within tolerance, then it says, okay, fine, I will use the additional information from that new Recordine run, and then I will create a new meta model, which is very fast to do, and then I will calculate a new optimal point. And it will continue to do that until the predicted behavior is within tolerance of the actual behavior. And this ends up being sort of a line search. And so the idea is that the DOE is covering a big design space, but it focuses in on a certain location based upon those results. And then with this evaluation to the optimal point, it will then focus in and then follow a line right to the optimal value. So this is one way of looking at it. The conventional meta model approach involves a lot of resampling, as shown as the top. So you have an initial DOE sample with a certain number of runs, which in some techniques they require a lot. And then based upon the results, as they adjust the parameters for the next search, then they're doing resampling everywhere. And you can see that with all these resamplings, then there's very many runs that are required. Well, if you have a complex system and a run takes an hour or a day to do, it's not reasonable to have hundreds and hundreds of runs required. So with AutoDesign and Recordine, we have a progressive meta model method. So we do a very efficient DOE with kind of a minimized number of runs that we have to do. And then as I've explained, with each new design, we're adding one data point, and that's used to update the meta model as shown here. And then that's done repeatedly until we converge to a solution. And then if you look at the total number of samples, as I mentioned, the samples are going to be, within one fairly close area. The samples, these red samples that are associated with the final convergence, because the DOE helped us get to the right starting point. So now with design variables in this process, as we've mentioned earlier, we define these design variables and all these different attributes. We design the performance indices, and then we take that information and look at how to then specifically define those things within Recordine. So design variables are mapped to parametric values, and parametric values can be defined either in the parametric value list, or you can derive parametric values, parametric point, in this case 10 could have, it is .x, .y is, coming from the parametric point. So both things can be used to define these design variables, and then again, you set the ranges and so forth. And then for the outputs of interest, again, defining these expressions and just using the standard expression functionality. So this is how then these steps are done. So in the user interface, we go to the parameter group, then pick the parameter function, and then we'll go through and define these design variables. And you can see all the different attributes that are assigned, lower bound, upper bound. Here's the current value. You can add a description to each one, and you can add some cost information and so forth. So with the create thing, the way you associate with it is a PV button associates with a parametric value. So then you pick that, and then you can add the additional information. And then with analysis response, you just pick that option as you create. Then you're going to reference the expression list, that you're familiar with, when you, for example, associate an expression with a motion. In Recordine, you have the same button, EL, for expression list, and then you just pick that expression that you've defined. And then with regards to these expressions, you have the regular basic expressions, but you can also reference information, finite element results. You can also reference scopes that have been defined, and you can also extract information from a process net function, and we'll see more about that later. Okay, now next step is to select the optimization approach and just, set the parameters associated with it. So we have these different design variables have been defined, are available to us. And then we have the performance index, and we can select them as we've defined them. And then for these performance indices, we can indicate whether or not they're going to be a constraint or objective function just by a pull down. And then depending on what it is, if it's some kind of constraint, we might say the value needs to be less than 4,000. Or we can have an equality constraint where the value needs to be at a value of 0.5. So, for certain goals that you have to achieve, you can you can define those as constraints. And then for things you just want to be the maximum possible or minimum possible, then those would be objectives. So then if you go to the optimization control tab, under methods, you can just stay with this auto selection. The first part of this is the DOE method. It can be very helpful to use this Latin hypercube design. It's very efficient, but there's other options that can be selected. And then on convergence tolerance, it'll suggest different values here, which are typically quite reasonable values, but you can adjust those as needed. This maximum number of SAO, SAO is the process of doing the additional runs after the DOE, and you can set a limit. And typically, if you get up to 100 evaluations, that means the system is probably not going to converge. So 100 is a good maximum value, but once you have experience in working with your own products, then you'll have a feel of how fast it will converge. And if things typically converge, like say in 12 SAO iterations, then you might want to set this maximum iteration value to, like, say 20, because in your case, once you get to 20, then it's probably not going to converge for whatever reason. So then after the run is complete, there's a variety of custom outputs that are produced. On the left here, we see this chart that shows the convergence during the SAO process, doing those iterations. There's also summary sheets that have been prepared to show you, what are the optimal values of the different design parameters. And so you can, look at the optimal value versus the bounds and so forth. There's actually, this optimization history that's available. So there's a lot of outputs custom to the optimization to help you see what's happened during the optimization. So we're going to quickly go through 6 different examples just to help you understand what a typical process is to come up with the design parameters and so forth. So this one's a truss bridge. Here we see the starting definition. The bridge is symmetric. So we have these locations. that are design parameters is labeled here. So we have a certain maximum load, 50,000 newtons, that worst case is when it's in the middle of the bridge. And we have certain constraints, allowable load on joints. And so what we want to do is we want to minimize this load applied to the joints because we want to have, factor of safety as high as possible. But we want to keep the cost under control. So we want to limit the total length of the links. So we're going to try to minimize that total length while also minimizing the load. And we're going to allow all these positions to change. So that's our basic problem. So then the design variables are all these different joint locations. When we look at the performance indices, basically we have a reaction force that we're going to track. And then, we're also going to be tracking this total length of the links. So we're going to minimize this reaction force, the maximum reaction force. We don't know ahead of time where the maximum reaction force will occur, so we have to have an expression that will tell us that. And then we can, as we saw, we can add up the total length of the links based upon the position. So in the multi-objective optimization, if you can only do a single objective function, like in the case with some products, you could do something like saying, hey, the optimal length is going to be 45, so let's optimize to there. But in our case, we want to actually look at two things at once, both the force as well as the length, because we want to be able to maximize factor safety and minimize cost at the same time. So when you map it actually into the AutoDesign interface, it looks like this. So these are the different points, X and Y coordinates, so point 2, point 3, and so forth. Those are all the different design variables. And then the performance indices, we have these two different analysis functions, and we're going to minimize one, but we're also going to apply a constraint that it has to be less than this 80,000 Newton max load. And the reason we do that is that, since, it's going to try to minimize, but we want to have a limit of what the maximum value is. So that's why we can apply the same performance index or the same analysis result in two different ways. One is an objective, one is a constraint. So AutoDesign is very flexible to allow that to happen. So this video, we can actually see how the bridge is morphing into different shapes as it's walking through the design of experiments. And as it, tries out all these different options, then that will provide information to indicate what is going to be the very best configuration. So with this particular model, we're actually doing 100 DO reruns, and then we're going to let it then do the optimization, and we'll see that it converges in 6 SAO runs. So, and again, SAO is sequential approximate optimization, meaning it's walking through the design space, with an approximate optimization, and then when it converges with the actual optimization, that's when we know we have a solution. Okay, so this is showing what happened. The top diagram is showing the initial bridge. And you can see, kind of this, flat profile and so forth. The length of all the links is 46.63 meters. The maximum reaction force is 111,000, way beyond our target goal of the 80,378. So if we just manually applied some kind of an arc or something, we could get to some kind of solution, but the question is, how would you even know to do it like that? But with the optimization, we're able to come up with the notion that this kind of a shape is the best shape, which, so maybe we're gaining design insights that we wouldn't have had before. We're able to, have a total length of all the links that's actually less than the starting point, while greatly reducing the reaction force, as we see here, even beyond the target. So we're down to 79,000 and some newtons. So that shows the power of the optimization. Okay, now we're going to look at the second example. It's four-wheel drive loader. We're looking at the hinge joints here in the center. And we're going to apply a load of 10,000 newtons at the bucket. But we're only going to allow the stiffnesses, in the 6 degrees of freedom of the joints to change. So here we see the loader in operation. It's just accelerating to a certain speed. And so we want to balance out the loads between the top and bottom, and but not have a displacement in the bushing exceed a 0.5 millimeter. So again, details, we have a predefined motion of the bucket. We have this load. We're accelerating the vehicle to 2.1 meters per second, and then hold that for 3 seconds. We're using a certain tire model, the UA tire, and then you can see how the stiffnesses of the bushings are reflected here in these parametric values. So we have 5 different degrees of freedom in the bushing that we're going to look at. The rotational stiffness in the intended degree of freedom of rotation, that's not of interest, because that's 0 stiffness, because it's free to rotate with this, with the revolute joint. So here's our design variables. So actually, we can reuse some of these design variables, because the radial, aspect is going to be the same in 2 directions. And then there's axial stiffness, which is in a different direction. Anyway, so we're trying to keep the design variables to be, as low a number as possible, while covering, the different aspects of interest. So we have the upper, and then this is showing the upper bearing stiffnesses, 3 of them, and then lower bearing stiffnesses. Okay, and then the performance indices, we're looking at the difference in the reaction forces between the 2. We're trying to maximize the factor of safety by spreading out the load between the 2 bushings. And then we're trying to make sure we keep these displacements under control as indicated. So the difference is an objective function. We're trying to make as low as possible. And then these other 2 are constraints because they have to be less than 0.5 millimeter. So now you can see how this is defined in Recordine. Current values, lower bound, upper bound. You can see that all these are defined in a similar way, upper and lower bearing, because they have a similar starting point. And then this shows how we can just use the pull down menus to define these constraints and objective functions and set up the goals. So very straightforward to define this. So in doing the optimization, we actually did 51 DOE runs, and then the SAO optimization ran through 49 steps. And so we started out with a huge difference in the load between the upper and lower joints. And after doing the optimization, we got the difference in the load down to 1%, which is a huge decrease. And so that makes really the bushings, it's going to increase the life because the load is spread out. And, with the answer that we got, the displacement was in the acceptable range. Okay, third problem is satellite deployment. We can see this animation. These panels are being deployed out. This is a solar panel. And the question is, how quick can we deploy this set of panels here while not exceeding certain joint loads. And also we want to have the system not only deployed, but have it be basically at equilibrium. So if we were to deploy things carelessly, we might end up with a large rocking motion, and that's not good because it causes high loads. So the allowable acceleration is needs to be kept within 0.4 G because of the different factor safety requirements. So when we look at what we're trying to optimize, we're looking at the joints between panels, and we also have a joint at the attachment point on this component that deploys. So where I'm pointing to with the arrow, that's where the solar array is attached to the body of the satellite. And so then things deploy out, and then there's going to be revolute joints throughout with each panel. And with those revolute joints, then we can have certain springs and so forth. So then we want to be able to define stiffness and damping values throughout. And we have a requirement that the deployment should be done within 60 seconds. So, we can't have things be so gentle that it takes, hours to deploy. That's outside the design requirement. So the acceleration we'll be looking at is each one of these individual solar panels. We have to track all of them. So then we can see the design variables. We're looking at these rotational springs, and then we'll be looking at the rotational damping. And so we have a set of values here. In our planning, we can see that the cost to change things is going to be the same for all the springs, and the conceptual difficulty is also low. So the performance indices, so we're going to look at the settling time panel to panel, and that needs to be within half a second, and we want to minimize that time. But the time to complete the total deployment is that, I think it was 30 seconds we were looking at. And then we have this maximum acceleration that we have to control. So then in mapping that into Recordine, we can see this is the AutoDesign panels. So we just simply apply all these design variables with the lower and upper bounds, current values. We can see these are the 5 different stiffnesses for all the joints between the panels. And then performance indices. So the time difference, we can, in this case, we're going to make a constraint that is actually equal to 0.5 seconds. And then the settling time, we want to minimize. And then the maximum acceleration has to be less than or equal to. So the 4,000 is our 0.4 G. So often, we're using these expressions to come up with the performance indices, but we do have the option to use, the user subroutines or the process net. So this shows a C# subroutine that's used to come up with the final settling time, looking at all the different panels. So this is C#, it's done with ProcessNet. These are standard ProcessNet functions. So, we're looking at the output of the simulation, the get plot data lets us go, and this is an expression to measure, what's going on with the angle between panels. And so then we're going to monitor that, and based upon that data, then we can come up with these different settling time values, and then we can use that information to determine the maximum settling time between all the joints. So that option's available. So we can see the optimal design deploys very quickly. The initial design, takes a very long time. So in this optimization, we did 21 runs for the DOE, and then we did 50 runs on the SAO to converge to the final solution. And settling time between panels went from 40 seconds to a half second. And that was a constraint, so I had to go to a half second. The settling time of the entire solar array went from 50 seconds to 8.6 seconds. And acceleration between each panel went from 0.414 G, which was above the target, and actually went below this target acceleration, even with the very fast deployment. So we can see there again. So it deploys quickly. You can see a little bit of motion there. But it's kind of motion of the entire array. So focused on one location and then settled out pretty quickly. Next is a hand press. So we have this linkage. We want to be able to pull this lever down, and we want to minimize the maximum resisting force, but at the same time, the load has to be high enough to be able to, have the lever pull back up, when the operator releases it. So, so that's, the trade-off here that the optimization has to deal with. So we can see this in the animation. It pulls down, and then when it's released, it does come all the way back up. There's a little bit of bouncing there. So looking at the details of the model, we can see that the critical thing we have here is a spring that connects into this wheel. And with this spring, the left end is fixed, but the right end that's attached to the gear, it can be moved to be anywhere on that gear. And then the displacement we're working through is to just go from the starting position down to where the press is totally seated on the bottom die there. So that's what we're trying to accomplish. The design variables have to do with the attachment point of the spring. And, this is basically a positional information around the circumference of the gear. And then preload, the spring has to be defined. What is the starting preload? And then another design variable is the force required for the operation. So basically, we'll force the motion and then track what the maximum force was. So therefore, the force required for an operation is derived. And then the end position of the press head, it has to go down 4.8 millimeters. And this lower position of the press head is, minus 32. So it has to be less than this minus 32. And then this, this thing has to be greater than 2. So the top two are constraints, and the bottom one is the objective function, trying to minimize that force. So we can see how we map that into the AutoDesign interface. So the values as from the previous slide are just placed into the dialog box, and then again set up the two constraints and then one objective function. So we did 50 runs with the DOE, and then it took just 7 runs on the SAO to converge. We were able to reduce the maximum force by 15%. And, basically everything else satisfies the constraints. And this just shows the stroke of the pressing head here. So that's been modified a little bit, but the key thing is it gets to the objective just in a little bit different way and is able to reduce the force by 15%, which is substantial. Next one is a kind of a Segway type vehicle, so two-wheeled vehicle. What we want to do is achieve a certain velocity, and basically the controller that's in place is not able to achieve that velocity. So then what we want to do is do the optimization to be able to close the gap between the target velocity and the actual velocity. And then some of the conditions, of course, the driver has to be in a safe posture. And, basically the goal is to get up to this 2 meters per second. So the details, we have revolute joints we're going to track for the 2 different wheels. So we'll track the velocity in those revolute joints, and then we have a controlling torque applied at the revolute joints. So the controller, there's actually 2 aspects of it. One is a controller that's trying to maintain the upright posture of the person, and the other one is controlling the actual torque applied to hit a certain pitch angle, but over you change that with time, and that becomes the velocity you're controlling. So those are the different control aspects under consideration. So then if we look at our tables, we basically have gains that we want to define on the controller. So it's a PID controller. So we have the proportional gain, integral gain, and derivative gain. And then the objective is to minimize this speed difference. So now if we look at how that's applied in AutoDesign, we have the 3 design variables with the PID gains, and then just simply the objective function. So so basically the DOE, we had 31 runs. The SAO converged in 3 iterations. With the optimized design, we can see the proportional gain went from 10,000 to 500. Integral gain went from 10 to 870. Derivative gain went from 10 to 608. And we were able to, the speed difference, you can see here's the initial speed difference, and we were able to reduce it, as you can see, substantially. The last model, simply, we're not going to go through every step because I think you're familiar with that, but just to say that you can also do the stress optimization. So this one, we're looking at the connecting rod being a flexible body. This is a demo model, so it's very simple. But we have a video here. So if we look at what's happening, you can see that we can set things up in Recordine with the design parameters to be able to morph that mesh, to take on different shapes, and basically we're walking through some of the different DOE steps at this point. And anyway, so the simulations in this case with FLEX, are running very fast because it's a simple demo problem. But maybe in an actual mesh, it may take some number of minutes or even an hour to do each run. And this isn't showing the whole process, but the idea is you do the DOE runs, and then it converges based upon the information. And the key aspect, if we look up here at this panel, this analysis results, we're actually able to inquire on stresses throughout the mesh. And so we can find out what the maximum stress is. In this case, we're going to map that to be a constraint, has to be less than 114. And then what we're trying to optimize is we're going to minimize the mass of the connecting rod. So this does give a good answer, but we're just not going to walk into all the details here. So in summary, as we know, design is a process for developing a reasonable product, meaning all the design specs are met. But with optimization, we can try to improve the performance and come up with maybe the best possible product, at least, given the product aspects that we can consider. There's 3 main factors involved in defining an optimization problem, which is to define the design variables, objective functions, and constraints. And formulating the requirements is really a key to optimization success. And, we've looked at a variety of optimization examples, and you can see that AutoDesign is able to handle many different problems, and it does so efficiently enough to, be a reasonable process to pursue. So, finally, please feel free to contact me or anyone else at EngineSoft. If you're interested in doing this optimization, we can certainly provide you with the trial of AutoDesign, but more than that, we're ready to work with you to help you apply the product and, kind of help you through having your first success. Because it is a little bit a different thing to do if you haven't done a system level optimization before. And so, we can get you started. And once you see what the process is for your particular product, then I think you're going to be in good shape to then continue to do optimization on your own. So at this point, I think I'm done and we're ready for questions.
Brent, I know one piece of feedback that I often get when somebody is looking at this toolkit is that it can be a little bit daunting for your first analysis. Do you have any suggestions for how somebody gets started? Are there any tutorials built in that somebody can kind of use as a starting point?
Yes, so there are actually, many tutorials. I think at least like a half a dozen different tutorials to try out with AutoDesign. And so, yeah, certainly you can get started by going through those tutorials. And then again, as you make the transition to doing, your actual product, then at that point we can step in and help you, go through the process. Because the tutorials will, help you quite a bit, but the initial mapping of your particular product and its characteristics, to these different design variables and objective functions and, the performance indices, that mapping is still going to be a little bit challenging, at least typically, even after doing the tutorials. But there are tutorials and they're great. So yeah, it's I think we have a pretty well established process to help our customers be successful.
I checked the YouTube comments. I don't see any questions in the chat there. And I'm not seeing any others on the Zoom interface. Let me take a quick double look. If anybody wants to add any questions, like we mentioned at the beginning, you can sign into YouTube if you're watching on there and post something in the chat. There's also a Q&A box. If you kind of move your mouse around on the Zoom interface, you should see Q&A towards the bottom there, and then we'll get that message there. Just trying to think of any other questions that I typically get when I kind of show off this functionality to people. I think the biggest one is probably, just getting started. There's a lot of little moving pieces, but I think, once you get the hang of it, like you had mentioned, once you do it the first time, it's a lot easier. Right.
Okay, great. So I think we're here at the end. So our final comment is we have been recording this, so we will make it available on the EngineSoft website. So if you'd like to share this presentation with any of your associates, it will be available for you to view, and we'll follow up with an email to you and let you know how to access the recording once we have it posted on the website. So with that, anything else, James?
No, I think that was the only other comment that I had, that we'll make it available. So
okay,
we really
great.
appreciate everyone's time.
Yes. Thanks very much, and have a great day.
All right, take care, everybody.